Hello everyone, welcome to Tactica Imperialis and to today's video. Today is going to be one of my Tactica Tutorialis science lesson videos, and today is going to be a GCSE physics or triple science lesson where we have a look at the sun and the structure of the solar system. Yes, it's time to talk about space. Now, I know this is a GCSE physics topic, so it's only examined on triple science exams. However, even if you're not a triple science student, this is still a really cool topic, and I thoroughly recommend that, particularly for space, you stick around because space is cool. Well, I find space really cool. I love astrophysics, so this is definitely, hopefully, going to be quite fun for all of us. But in today's lesson, we are going to do the sun and the structure of the solar system. Now, it's more than just, here is a sun, here is some planets. There is more to it than that. I'll preface that now. So we're going to go over what makes up the solar system in general and pretty much in totality. And we're also going to look at how the sun works in sort of an overview sense. We're not going to get into the life cycle of stars particularly. That's a separate lesson in and of itself that I'm more than happy to do in the future. And we're not going to get too much into the mathematics of the nuclear reactions that go on within the sun. That is a lesson and a topic that I'm going to tie into a future lesson on nuclear fusion, which when I've done it, I will link in the description. It might not be for a couple of weeks. But there is still plenty here, so make sure you have your pen and paper and a pencil if you are writing things down, because there is definitely going to be drawings and diagrams as part of this lesson. And if you're working on a computer, make sure you have everything set up to get yourself a cup of tea if that's your thing, though be careful not to spill it. Any solutions for any exercise that we do will be at the top of the description for whenever I ask you to do them. Make sure to check those so you've got your answers in order before moving on with the lesson, because everything builds on top of itself when it comes to space. But with all that said, and without any further ado, class is in session. Let's begin. So to get us started for today, I'd like to have a quick recap of things that you may know about space already before we dive into the full details of the solar system. And one of the things that I think most people know or have come across in earlier education is the concept of the fact that there are planets. So what I would like you to do, just to get your brains warmed up for about 2 or 3 minutes, is I would like you to write down the names of the planets in the solar system. And if you're feeling a bit more confident, or you get that within time, I'd like you to put them into order, if possible, of distance from the sun. So you might just write them down as a random order the first time, and then in your second list or your final list, you'll write them down with the closest to the sun first on your list, and you go across or downwards, and the furthest from the sun will be last on your list. For those who have forgotten or are a bit behind the times, I'll give you a hint there. There are 8 answers to this question, not 9, and I'll explain that a bit in the solutions video. So have a go at that for 2 or 3 minutes, and then once you're happy, you can have a click of the top link in the description to the starter solutions, where we'll go through the correct answers, and we'll also have a little bit of a chat about some history, because I love the planets and I think it's a fun conversation. So 2 to 3 minutes, off you go. So now that we've got our head around the planets a little bit, check the link in the description if you need a reminder. Let's have a talk about the wider solar system and what you can find in it. One little bit of bookkeeping. I'm not going to say the word the solar system 100 times, and I'm certainly not going to write it 100 times because I haven't got that much space on my whiteboard. So whenever I make reference to Sol, I am referring to the solar system. It is just a quicker shorthand. I'm not actually sure if that's its official classification, but it is certainly close enough, and long-time viewers of this channel may obviously get the reference. So, what do we find within the solar system? Well, largest of all, we find the sun. The sun is a star. In fact, it is what we call a main sequence star. Now, I'm not going to explain what that means here. In fact, we'll talk about the sun a little later in today's lesson, and we will talk about the life cycle of stars in another video, perhaps, if you would like me to cover that in the future. But that means it has a certain age, a certain size, certain properties, and a certain fate. But again, we're not getting into that here. It is also the heaviest and largest object in all of Sol. Heaviest and largest. object. Therefore, it has the highest gravitational field. Now, I've done a lesson on G fields before, but that is an A-level topic, so the mathematics of G fields you don't need to know. What you need to know about gravitational fields is stuff you'll have met before in concept. They pull objects in towards them, and the sun having the largest one of all means that it is able to hold more things and pull more things in towards it. And because these objects have their own gravitational fields, it means that that ends up with orbits. And because the sun is the largest, everything orbits it. So everything else in Sol orbits the sun. Everything does. The sun can pretty much be found at the center of the solar system because all orbits go around it. Therefore, you'd have to get your rulers out and work out if it was exactly in the middle, but roughly, it's pretty much bang in the middle of the system. Following on from that, once you go inwards from the sun, so you sort of zoom in a little bit more, the next thing you're going to find is a planet, or a series of planets, actually, the 8 that we have discussed. So the planets are large objects, and there are 2 main types of planets. You've got rock planets like the Earth, or what we call gas giants like Jupiter and Saturn, that some of them have got rocky surfaces and have got metallic cores like the Earth does, and the gas giants have neither of those things. They're mostly just big balls of gas. In fact, a lot of the gas giants are larger than the rocky planets because, well, in the case of Jupiter anyway, they had the potential to become stars. Jupiter actually nearly did, but it wasn't quite big or heavy enough to get that going. But we'll talk about that another time, I think. And these things orbit the sun, obviously. But what defines a planet versus a place like Pluto, which is classified as a dwarf planet, is their ability to what we call clear the neighborhood. Now, you might think, what on earth are you talking about? Like, we don't have, like, Planets Row or something where all the planets live together and try and coexist. And no, we don't. So what I mean by that is that their orbit is broadly empty. So they like clear out or pull in a lot of objects and debris and such that are on their orbital path. That's not to say that things can't orbit a planet. Obviously, things can orbit planets. Obviously, our satellites do it, the moon does it, and many planets have moons, actually. But it means that on their sort of orbital path, you won't find just random clumps of space rocks. The Earth has cleared them out during its orbit, and all planets have done it. And that is why Pluto is no longer classified as a planet. It is classed as a dwarf planet. So they're like planets, but smaller. And what that therefore means is that they're not able, because they're not big enough, they're not heavy enough, their gravitational field is not strong enough for them to be able to clear the neighborhood. Which means that if you were to have a look at Pluto's orbit, you'd find other rocks and debris and bits and bobs within its orbit. Whereas if you went around Earth's orbit until you got back to Earth, you wouldn't find such things. And I'll give you a couple of examples of dwarf planets. Obviously, the most famous one that we have these days is Pluto, because it was formerly known as a planet, but it was reclassified a few years ago. And there is one in the Martian asteroid belt. I think it's the only one that's big enough in the Martian asteroid belt, known as Ceres or Keres, depending on how you prefer to pronounce it. And they are dwarf planets. They're like planets, but they're smaller. They don't really have the ability to maintain an atmosphere like planets can do. Well, most planets can do. And they can't, most importantly, clear this neighborhood and get their orbits clear of junk, or get their sort of orbital path cleared of all junk. So there's your first set of notes on sort of the larger objects within Sol. I'm going to clear this and then do a quick jump cut, and we'll talk about the remaining objects once you've taken this down. So the next set of objects out in Sol, once you've zoomed in past the sun, so let's say you were looking at the universe, you would then zoom in to find galaxies. Well, you'd actually find something, I think, beyond even galaxies. And you get into the Milky Way galaxy. Then you zoom in from there, and you find, eventually, Sol in just the right place. And then you zoom in from that, you find the sun, and then the planets, and then roughly on the same tier as the dwarf planets, you will find what we call moons. Not just the moon, there are many, many moons. So moons orbit planets. So yes, they do orbit the sun because they do go around the sun, but their orbital path, if you like, goes around a planet, which is also going around the sun, if you like. And they are known as satellites. So the term satellite actually outdates the technological equipment that we have put up into our planet's orbit. So satellites orbit planets, and some have none. Some planets have none, some have loads. Have few / no moons. So for example, the Earth only has one, but others have several. And I do mean that in terms of, it's not just like 2 or 3. I think Jupiter and Saturn in particular have a lot of moons. I'm not going to list them all off here, but there's ones like Europa, Titan, as moons of Jupiter and Saturn respectively. Mars, I think, has 2 moons, as I recall. So moons orbit planets, and that's sort of their classification. And the reason I'm putting them after dwarf planets is because you only find them around planets. However, I would wager that there are some moons that are actually on the same sort of size scale as a dwarf planet. They're just stuck in an orbit already around a planet, and thus they don't count as being in an orbit all of their own. I wouldn't be surprised anyway. Next down from that, if you zoom in again, you will find what we call asteroids. So asteroids are slow orbiting space rocks. Slow orbiting, small rocks. Asteroids are actually very, very boring because they are not the things that go blasting through the sky sometimes, or across the skyline through space. That's not an asteroid. Asteroids look a lot more often just sort of sit there. They sit in their rough orbit in space, and they just go around very, very slowly. And you often find them in what we call belts. E.g., between Mars and Jupiter. So I talked about in the solutions video for the start of the fact that there's a gap between Jupiter and Mars, and there is. And in that gap is not just empty space, there is actually an asteroid belt sat between Mars and Jupiter where you'll just find a giant pile of space rocks. So getting past Mars and out to Jupiter is actually quite awkward unless you're able to leave the sort of what's the word I'm looking for? The solar plane, as it were, because most planets are actually sat on kind of a planar orbit. I'm not getting into that today. That gets into all sorts of very high-level physics that I don't have time for, and you don't need to know. So if an asteroid is not that thing that goes flying across the skyline and causing everyone to go wow on the internet about it, what are they? Well, those objects are known as comets. So a comet is a fast-moving, or fast, I'll put faster, moving and non-orbiting slash wonky orbit rock. So comets actually are not kind of like the Earth, where it's roughly a similar distance from the sun all the time. The Earth's orbit is not a perfect circle. In fact, it is more of an ellipse, which is why the Earth is the way it is. But the orbit is roughly fine and constant. A comet's orbit is probably very wonky and very weird, if it even has an orbit at all. Sometimes it might just be a hunk of rock that comes flying through the solar system and gets too close to the sun. So it begins to burn slash disintegrate nearer the sun, which is why they can't have that nice steady orbit that planets have, because they get a lot closer to the sun, causing them to form what we call tails of gas. So very often, if you've seen those very cool images of comets blasting across the sky, or in films where people create these images of comets, you'll often see them burning up or with this big long streak out behind them. In fact, I'll sketch it for you because I feel like it. You might find that your comet looks something like this. It's just a lump of rock. And then you'll find behind it, so like whichever way it's moving, if it's moving that way, you'd find that it's sort of wreathed in like a corona, that's a bad choice of word at the moment, a sort of tail of fire or in general burning gas, because the comet has got so close to the sun and got so hot that it is starting to break up or fall apart, or the gases around it are catching fire, and so on and so forth. And it creates this sort of streak behind it. In fact, I've drawn that in completely the wrong place, because that creates the idea that that's an asteroid. That's not an asteroid. An asteroid is a very boring rock that just sort of sits there and you get lots of them in belts. That's a comet. That's not an asteroid. I've drawn that in completely the wrong place. I apologize. So those are the components of the solar system over the two segments that I've just written up. You've got the sun itself, then you've got planets, dwarf planets, moons, asteroids, and comets, which look like this. Should go here. They look like this. So if you're able to read that, take your time, pause the video, and write up the notes of the various components. I appreciate it's probably not the most fun thing for you to do, but it's a good way for you to get your notes locked into place. We're now going to do a quick little assessment activity so that you can just get an idea of these properties in your head and start matching them up a bit and describing them, and then we'll get into more detail and have a proper look at the sun itself. So, just to check your understanding a little bit of the components of the solar system, we're going to play a little game, a little riddles, sort of guess who type of game regarding the components of Sol. The solutions and the answers to these riddles can be found in the description, but I'd like you to have a go at answering each one before you go and check the answers. So there's going to be 3 little guessing riddles that I'd like you to answer. They're not particularly complicated. I'm not the riddler. And once you've answered all 3, go and check the link. I think it's going to be the second link down in the description to get your answers. So, our first stellar component. What's it going to be? Well, it is an object that has an orbit. So it orbits things. And it's usually made of rock. And the final clue I'm going to give you is that we, i.e. humans, have made things that share their name. Things with the same name. So that is your first one. So what do you think that solar system component is. It has an orbit, it's usually made of rock, and we've made things that have the same name as it. Number two. Number two doesn't really have an orbit. And you should probably look out for the tail. So what do you think that one is? Have a think about it. And the third one comes from a rather cluttered neighborhood. It comes from one of these cluttered neighborhoods, if you like. And you'll sometimes find it hanging out with asteroids. So those are your three little riddles / hints to work out the components of Sol, and to be fair, pretty much any solar system. So give yourself about 1 minute for each one, so overall 3 minutes if you haven't worked them out already. Write down what you think they are, and if you can, try and justify, even though you don't need to write it, try and justify in your head why they are the answers. So once you're happy, you've had your 3 minutes, check the second link in the description. It'll be linked as the What Am I solutions. And once you're happy with that, we'll move on and we'll have a proper chat about the sun. So now that we have a better idea of what the solar system is made of, how it all fits together, and granted I haven't shown you a planetarium to show you exactly how it fits together, let's have a bit of a zoom in and talk about the sun. This is not going to be a comprehensive, one-size-fits-all, everything you need to know about the sun. This is going to be sort of a history lesson of how the sun came to be what it is today, what it was when it was first formed, and a couple of things like that about how it works. This is not going to be, as I say, a full life cycle of a star deep dive. That is an entirely separate lesson, but it should give you some early insight. The first point I want to make about the sun, and I'm not going to write this as like a copy downable bullet point because I don't think it's that important, but the sun is a very average star. There is genuinely nothing that special about the sun. It's a very average mass, it's a very average size, it's a very average age. There's nothing that special about the sun, I'll be completely honest with you, in terms of stars in the galaxy and stars in the universe. So, the sun was originally a cloud known as a nebula. Actually, that doesn't need to go in air quotes, that needs to be underlined because it's a key word. A nebula essentially was a cloud of dust, gas, etc. And this is the same for all stars. All stars start out as a nebula. In fact, several stars can be formed out of one nebula if you get a bit lucky. And what sort of happened to a nebula? This started about 4.6 billion years ago. So that little wibbly symbol is roughly, approximately, 4.6 billion years ago. YRS ago. It condensed and was pulled together by gravity, because even though it was a cloud of dust and gas, every object has gravity, has a gravitational field, and they all attract each other, and they pulled themselves together over a long period of time, roughly 4.6 billion years ago. This led to a protostar. So it wasn't a full-blown star yet. So what that means, a protostar is hot, dense, but no nuclear fusion. So this actually crosses over with another topic, the idea of nuclear fusion, which I'm not going to explore at great depth here. That is definitely another story for another day. And this is what means that we had a protostar and not a star, because the density and the mass and the gravitational field of the protostar was not yet great enough for nuclear fusion reactions to happen, because nuclear fusion requires exceptionally high energetic conditions, high pressure, high temperatures, and a protostar just doesn't quite have that. I think actually we're a bit beyond something like Jupiter, which many suspected could have gone on to become a star, where it's a bit bigger and a bit heavier. But I wouldn't class Jupiter as a protostar. It's a planet, just a very big gas giant planet. Eventually, and I don't want to put an exact number on this because I'll get it wrong, eventually became hot and high pressure enough, or high pressured, I should say, enough. It's not my best piece of English, so forgive my grammar. The protostar became hot enough and had a high enough pressure for fusion of hydrogen, because that is the lightest element, the easiest element to fuse together, leading to formation of a star. The protostar now had its nuclear reactor going, if you like, and so it was able to do nuclear fusion reactions, meaning it was no longer a protostar. It could be classified as a star on what we call the main sequence, which means that it is undergoing hydrogen fusion. Now, there are other stars that do different types of fusion, and we could explore those in a future lesson if we do the life cycle of a star. But stars like the Sun, the majority of stars, for most of their life, live on the main sequence, where they are doing hydrogen fusion to turn hydrogen into helium, and that goes on and 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 on until the Sun runs out of that, and we'll get to that another day, I suspect. But you might be thinking, but Tactica, I've got a giant ball of gas that is super duper heavy, and we know it's super heavy because it collapsed in on itself to create this nuclear reactor, to create the protostar in the first place. So why hasn't it all collapsed in on itself? Well, dear student, what we say is that the pressure, and I'm going to put a word in brackets here that you don't need, but I'm going to write it because you might come across it if you take physics further. Something called hydrostatic pressure from the fusion balances collapse due to gravity. Gravity, therefore, stable shape and form. So if gravity was the only thing working on a star or on the sun would collapse in on itself. It would just keep collapsing and collapsing and collapsing because the gravity was pulling all of the gas particles inwards, and while it might create the fusion reactions, it's still collapsing in on itself, and eventually it would all just collapse into as near to, not a singularity, that would be unfair because you get those after stars explode, but, well, sometimes after stars explode, but it wouldn't allow the sun to stay the way it is. It would constantly be collapsing and collapsing and pulling things in from around it, and so it wouldn't be working the way it does. But those nuclear reactions that are going on, that fusion of hydrogen, and it's not like, oh, there's just one or two reactions going on. There are billions, trillions, trillions of trillions, a trillion times a trillion, and so on. I don't even want to know how many nuclear reactions are going on in the sun at any one particular second. But there are so many nuclear reactions going on in the sun that the energy they are releasing and the forces they are releasing by this nuclear fusion is creating a pressure inside the star that is pushing outwards. It is an expanding, like, pressure wave almost that is pushing back and balancing the forces of the star's own weight that are causing it to collapse in on itself. So the pressure forces of the reaction, this hydrostatic pressure, as I'm going to call it, that's a degree term, by the way, don't worry, are pushing outwards as the forces due to gravity are pushing inwards, causing the star to eventually balance its forces and thus stay roughly as it is, a decent-sized, massive ball of gas. If the nuclear reactions were to stop, then the gravity of the situation and the weight of the star would cause it to collapse in on itself until more nuclear reactions could get going, and then the star would expand again. And that is what is going to happen to the sun when it eventually runs out of hydrogen in whatever year that happens to be. It will collapse in on itself a bit, and then it will get helium fusion going, and that will cause it to blow up again to a bigger size. And actually, if I remember correctly, it will fully swallow up the Earth. But that's a story I heard. I can't verify off the top of my head, but you're welcome to look into what happens when the star runs out of hydrogen. But that is all the story for another day with the life cycle of a star. I'm not going to go any further than that. So that is everything you need to know about the sun in shorthand bullet points. So if you want to copy that down, we're going to have one last little quiz exercise just to check your understanding before we wrap up for the day. All right, so now that we've got a better idea of the sun, let's talk about solar energy. This is going to be our final task for today before we properly just wrap a few things up. So what I'd like you to do is consider the energy transfers that happen in the sun. There's a lot of them, and there's been lots of them throughout its life so far. But can you identify those energy transfers? So what I'd like you to do is write down the energy transfers that take place during the collapse of a nebula, and if you're feeling a bit more confident and you know your nuclear physics, the fusion reactions in the sun. So there are two parts of the nebula, and this is probably the bit that I expect everyone to be able to have a go at. This one's a bit trickier and you might not necessarily need it the same. So when the nebula is collapsing, there are two sort of stages. There's as it's collapsing in on itself, but before a protostar has been able to form, and then you think about, okay, it's now collapsed, or is collapsing, and what has happened now that a protostar has been formed, thinking about what a protostar is according to its definitions that we talked about earlier. So I'll give you a short hint. This one, you start with one star and you end up with another star, so it's 1 to 1. With this one, it's 1 to 2. So you'll start off with a particular star, and then you will end up with 2 different stars at the end. And these 2 steps follow on from one another. So the answer to this one, the final star, is the beginning, there's the initial star for this one. So those are your hints for this one, because it's quite tricky, but I feel confident you can have a go at it. With the nuclear fusion reactions, there's definitely one star you should be able to work out as the final star, but you may consider there to be a second depending on how you've been taught about energy types, energy stores, and so on and so forth. So that was a little bit trickier, but I will let you have a go at it. So give yourself about 5 minutes to have a go at it, and then check the third link in the description, which will be the energy solutions. Click the link once you've had a go at this exercise, and then once you're done with that, we will properly wrap things up. All right, let's wrap this thing up then. This is going to be a final task, though it's not one that I think needs to come with solutions, so there won't be a link in the description for this one. But what I'd like you to do is a final task. You can easily check this by looking it up online. So what I'd like you to do is sketch, not to scale, don't worry, not to scale, the solar system. Using what we've done today, I would like you to sketch out for me a rough model of the solar system. You don't have to do it full 3D, clever animations or anything like that. Something as simple as this would suffice. You could do it almost as if everything was in a line. So you might have it with the sun out here as your star, obviously, and then everything else would flow outwards from there. So you could put the planets in. You could put in, so maybe label some of the dwarf planets, maybe label asteroids, maybe draw a couple of comets in there for good measure, but draw a rough model of the solar system working outwards from the sun using everything we've done today. You can easily check what this looks like. There are plenty of models out there on the internet, plenty of drawings that go into different levels of detail. And if you want to push yourself as an extension, label and describe the components. Because I know some people prefer to have written notes like we've compiled today with all the different components, but some would prefer to have it in shorthand diagram form. So to come back to our model of the sun, there's the sun, and we draw a little label to it, and we could say that it is a star. We could say that it was a nebula, which is what we did earlier. You could add any labels you want to it, as this might be a better way for you to compile your notes on the structure of the solar system than it would be for you to have them as a big long pile of notes. So it just gives you a different revision tool that condenses everything we've done today into a very small space that allows you to get the key points down using this and your other work. But either way, that is all for today. That is today's lesson on the sun and the structure of the solar system. And I do hope you found it informative, enjoyable, and useful. Make sure to go back through the lesson and complete any outstanding activities based on the planet layout, the components of the solar system with the little riddles, and the solar energy exercise. I appreciate there are varying degrees of difficulty, but please do have a go at them. The solutions are in the description if you want to check anything. In the comments below, if you have any questions following on from this lesson, please do feel free to ask them. And you can also make requests for future lessons. So I'd be tempted to do nuclear fusion based on what we've done today. I'd be tempted to do the life cycle of a star and other things to do with space if you would like. Orbits, for example, which could also transfer over to A-level if you're more interested in seeing it done there. So there's plenty of things that we can do to follow up on this, but I want to, of course, shape these lessons and the lessons I teach around what people would like to see. So if you have any requests, please do feel free to ask me in the comments below. But for now, thank you very much for watching. Class dismissed. This has been Tactica Imperialis, and this has been the structure of the solar system and the sun as part of our Tactica Tutorialis lesson. I'll see you all again. Bye for now.